What if the universe itself is hiding a secret so profound that it could rewrite everything we think we know about existence? Picture this: an invisible force stretching the fabric of space, pushing galaxies apart faster and faster, and yet we can't see it, touch it, or even fully understand it. This is the mystery of dark energy, the enigmatic force driving the cosmic dark energy era. Over the next few minutes, we're diving into 25 of the most mind-bending mysteries surrounding this cosmic phenomenon. From the accelerating expansion of the universe to the eerie possibility of a multiverse, we'll explore questions that challenge the very foundations of science. Why does dark energy exist? What does it mean for the future of the cosmos? And could it hold the key to unlocking the ultimate fate of everything we know? Stick around, because by the end of this journey, you'll not only have a deeper understanding of the universe's greatest enigma, but you might just find yourself questioning the very nature of reality itself. Let's begin. Now, turning to the first mystery, let's explore the groundbreaking discovery that the universe isn't just expanding, it's doing so at an accelerating rate. This revelation, made in the late 1990s, completely upended our understanding of the cosmos. Before this, scientists believed that the expansion of the universe, set in motion by the Big Bang, would gradually slow down over time due to the pull of gravity. But in 1998, two independent teams of astronomers studying distant supernova made an astonishing observation. These exploding stars, known as Type 1, a supernova, appeared dimmer than expected, suggesting they were farther away than previously thought. This could only mean one thing: the universe wasn't just expanding, it was speeding up. The implications of this discovery were profound. It meant that some mysterious force was counteracting gravity, pushing galaxies apart faster and faster. This force, later dubbed dark energy, became the centerpiece of modern cosmology. The finding was so significant that it earned the researchers the Nobel Prize in Physics in 2011. But what does this accelerating expansion mean for our understanding of the universe? For one, it suggests that dark energy makes up about 68% of the total energy in the cosmos, dwarfing the contributions of both dark matter and ordinary matter. It also raises questions about the ultimate fate of the universe. If this acceleration continues, galaxies will drift farther apart, leading to a colder, emptier cosmos over billions of years. This discovery didn't just change the way we see the universe, it forced us to rethink the very laws of physics. It challenged the long-held assumption that gravity would dominate the cosmic landscape, revealing instead that an invisible, repulsive force holds sway. And while we've made strides in understanding dark energy, its true nature remains one of the greatest unsolved mysteries in science. As we move forward, this mystery will continue to shape our quest to unravel the secrets of the cosmos. Now, shifting our focus, let's dive into the heart of the mystery. What exactly is dark energy, despite its overwhelming presence in the universe making up nearly 70% of its total energy? Dark energy remains one of the most elusive and enigmatic forces in science. Unlike dark matter, which we can infer through its gravitational effects, dark energy doesn't clump or interact with matter in any observable way. It's invisible, intangible, and seemingly everywhere, yet we still don't know what it truly is. One of the leading theories is the cosmological constant, an idea first proposed by Albert Einstein over a century ago. Einstein introduced this concept to balance his equations of general relativity, imagining a constant energy density filling space uniformly. At the time, he called it his greatest blunder, but today, the cosmological constant is a frontrunner in explaining dark energy. It suggests that empty space itself has an inherent energy pushing the universe apart. However, this theory comes with its own set of challenges. For instance, the predicted value of this energy is astronomically larger than what we observe, leaving scientists scratching their heads. Another intriguing possibility is quintessence, a dynamic form of energy that changes over time. Unlike the cosmological constant, which remains steady, quintessence could vary in strength, potentially explaining why the universe's expansion rate has shifted throughout its history. Think of it as a cosmic dial that adjusts itself, influencing the universe's fate in ways we're still trying to understand. But here's the catch: quintessence is purely theoretical, and no direct evidence has been found to support its existence. The challenge of studying dark energy lies in its subtlety. It doesn't emit light, absorb radiation, or interact with matter in any detectable way. Instead, its presence is inferred through its effects on the universe's expansion. This makes it incredibly difficult to measure directly. Scientists rely on indirect methods such as observing distant supernovae, mapping the large-scale structure of the universe, and studying the cosmic microwave background. Yet, even with these tools, dark energy remains a puzzle. So why does this matter? Understanding dark energy isn't just about solving a cosmic riddle, it's about unlocking the fundamental laws that govern our universe. It challenges our understanding of gravity, space, and time, forcing us to rethink the very fabric of reality. As we continue to probe this mystery, one thing is clear: dark energy holds the key to some of the universe's deepest secrets, and unraveling its nature could reshape our understanding of everything we know. Now turning to the cosmic microwave background, or CMB, we find one of the most powerful tools for unraveling the mysteries of dark energy. The CMB is often described as the afterglow of the Big Bang, a faint radiation that fills the universe and provides a snapshot of its earliest moments. This ancient light holds vital clues about the composition and evolution of the cosmos, including the role of dark energy. One of the key ways the CMB helps us understand dark energy is by revealing the universe's large-scale structure. Tiny fluctuations in the CMB's temperature map the distribution of matter and energy in the early universe. These fluctuations eventually grew into the vast cosmic web of galaxies and galaxy clusters we see today. Dark energy plays a crucial role in this process, influencing how these structures form and evolve over billions of years. By studying the CMB, scientists can measure the effects of dark energy on the universe's expansion and its impact on the growth of cosmic structures. The Planck satellite, a groundbreaking mission launched by the European Space Agency, has been instrumental in this research. Planck's precise measurements of the CMB have provided some of the most detailed maps of the early universe, allowing scientists to test theories about dark energy with unprecedented accuracy. For example, Planck's data has helped confirm that dark energy makes up about 70% of the universe's total energy content, aligning with earlier observations from supernova and galaxy surveys. But the CMB doesn't just tell us about the amount of dark energy, it also offers insights into its nature. By analyzing the patterns in the CMB, researchers can test whether dark energy behaves like a cosmological constant or if it changes over time, as suggested by theories like quintessence. These measurements are critical for narrowing down the possibilities and bringing us closer to understanding what dark energy truly is. As we continue to study the CMB, it becomes clear that this ancient light is more than just a relic of the past, it's a window into the universe's future. The interplay between dark energy and the CMB shapes the destiny of the cosmos, influencing everything from the fate of galaxies to the ultimate fate of the universe itself. With each new discovery, we move one step closer to solving one of the greatest mysteries of all time. Now shifting our focus to the Hubble tension, we encounter one of the most puzzling challenges in modern cosmology. This tension refers to the discrepancy between two primary methods used to measure the universe's expansion rate, known as the Hubble constant. On one hand, measurements based on the cosmic microwave background, or CMB, suggest a specific value for this rate. On the other hand, observations of nearby supernova and other local phenomena provide a slightly higher value. This inconsistency has left scientists scratching their heads as it challenges our understanding of the universe's evolution and the role of dark energy. The Hubble tension is more than just a technical disagreement. It's a mystery that could reshape our understanding of the cosmos. If the discrepancy is real and not due to measurement errors, it might indicate that something fundamental is missing from our current models. For instance, it could suggest that dark energy behaves differently than we thought, or that there are unknown forces or particles influencing the universe's expansion. This tension has sparked intense debate and motivated researchers to explore new theories and refine their methods. One leading hypothesis is that dark energy might not be constant over time, as the cosmological constant model suggests. Instead, it could evolve, leading to subtle changes in the expansion rate that aren't fully captured by current observations. Alternatively, the tension might point to the existence of new physics beyond our current understanding, such as modifications to Einstein's theory of gravity or the presence of additional types of dark matter. These possibilities highlight how the Hubble tension isn't just a problem to solve. It's an opportunity to uncover deeper truths about the universe. Efforts to resolve this mystery are ongoing, with scientists using a variety of approaches to refine their measurements. For example, new telescopes and instruments like the James Webb Space Telescope are providing more precise data on distant galaxies and supernova. Meanwhile, collaborations like the Dark Energy Survey and the upcoming Vera-C Rubin Observatory aim to map the universe's large-scale structure with unprecedented detail, offering fresh insights into the expansion rate and the influence of dark energy. As the scientific community continues to grapple with the Hubble tension, one thing is clear: this mystery has the potential to unlock new chapters in our understanding of the cosmos. Whether it leads to a revised model of dark energy, the discovery of new physics, or a deeper appreciation for the complexity of the universe, the journey to resolve this tension is as exciting as the answers it may reveal. And with each new observation and experiment, we edge closer to unraveling one of the most intriguing puzzles of the cosmic dark energy era. Now turning to the fate of the universe, we find ourselves staring into the vast, uncertain future shaped by dark energy. This mysterious force doesn't just influence the present expansion of the cosmos, it holds the key to how everything might end. Scientists have proposed several dramatic scenarios, each painting a different picture of the universe's ultimate destiny, and dark energy plays a starring role in all of them. One of the most widely discussed possibilities is the Big Freeze, also known as the heat death of the universe. In this scenario, dark energy continues to drive the universe's expansion at an accelerating rate, causing galaxies to drift farther and farther apart. Over trillions of years, stars will burn out and new ones will stop forming, leaving the cosmos cold, dark, and empty. The universe would become a vast, lifeless expanse with temperatures approaching absolute zero. It's a chilling thought, but one that aligns with our current understanding of dark energy's relentless push. Then there's the Big Rip, a far more dramatic and destructive outcome. If dark energy grows stronger over time, it could eventually overpower all other forces in the universe, including gravity. Galaxies, stars, planets, and even atoms would be torn apart as the fabric of space itself stretches beyond its limits. This catastrophic event would mark the end of everything as we know it, leaving behind a universe fragmented beyond recognition. The Big Rip is a stark reminder of how little we truly understand about dark energy's potential behavior. On the other end of the spectrum lies the Big Crunch, a scenario where dark energy's influence weakens, allowing gravity to take over. In this case, the universe's expansion would slow, stop, and eventually reverse, pulling everything back into a single, infinitely dense point. It's a cosmic do-over where the universe collapses in on itself, potentially setting the stage for another Big Bang. While this idea offers a cyclical view of the cosmos, it remains speculative, as current observations suggest dark energy is still driving expansion. These scenarios aren't just science fiction, they're grounded in the latest scientific theories and observations. Each one highlights the profound impact dark energy could have on the universe's future, from a slow, cold fade to a violent, explosive end. Yet, despite the dramatic possibilities, one thing is certain: dark energy remains one of the greatest mysteries in cosmology, and its true nature will determine the fate of everything we know. As we ponder these cosmic futures, it's worth asking, what does this mean for us? While these events lie billions or even trillions of years in the future, they remind us of the universe's dynamic and ever-changing nature. The study of dark energy isn't just about understanding the cosmos, it's about uncovering the story of our own existence and the ultimate destiny of all that surrounds us. And as we continue to explore these mysteries, we inch closer to answering one of humanity's oldest questions: how will it all end? Now, shifting our gaze to the multiverse, we enter a realm where dark energy takes on an even more profound role. Imagine a vast cosmic landscape, not just of one universe but countless others, each with its own unique set of physical laws and properties. This is the multiverse hypothesis, and dark energy might be the key to understanding how such a reality could exist. At the heart of this idea is the concept that dark energy's density, the amount of energy it contains per unit of space, could vary across different regions of the cosmos. In some areas, dark energy might be stronger, driving rapid expansion and creating vast, empty voids. In others, it could be weaker, allowing gravity to dominate and giving rise to dense, structured universes like our own. These variations could lead to a patchwork of universes, each with its own distinct characteristics, from the number of dimensions to the types of particles that exist. But how does this connect to the multiverse? One leading theory suggests that during the early moments of the universe, a process called inflation caused space to expand exponentially. This rapid expansion could have created bubbles of space-time, each with its own unique properties, including different amounts of dark energy. These bubbles would effectively become separate universes, each evolving independently within the larger multiverse. In this scenario, dark energy isn't just a force within our universe, it's a defining feature of the multiverse itself. The implications of this idea are staggering. If dark energy's density can vary, it raises the possibility that our universe is just one of many, each with its own version of reality. Some universes might be so dense with dark energy that they expand too quickly for stars and galaxies to form, while others might collapse back in on themselves before life can emerge. Our universe, with its delicate balance of dark energy and matter, might be a rare exception, a cosmic Goldilocks zone where conditions are just right for life to exist. This leads us to the philosophical questions at the heart of the multiverse theory. If there are countless universes, each with its own set of physical laws, what does that mean for our place in the cosmos? Are we the result of a cosmic lottery, living in one of the few universes where life is possible? Or is there something deeper at play, a fundamental principle that ensures the existence of life-supporting universes? These questions challenge our understanding of reality and force us to reconsider what it means to exist in a universe or a multiverse shaped by dark energy. As we explore these ideas, it's important to remember that the multiverse remains a speculative concept, one that pushes the boundaries of our current scientific knowledge. Yet, it's also a testament to the power of human curiosity and imagination. By connecting dark energy to the multiverse, we're not just exploring the mysteries of the cosmos, we're redefining the very nature of reality itself. And as we continue to probe these questions, we may find that the answers lie not just in the stars, but in the infinite possibilities of the multiverse. Now turning to the role of dark energy in the grand tapestry of the cosmos, we find its influence extends far beyond the expansion of the universe. It plays a crucial part in shaping the very galaxies we observe. To understand this, let's start with the cosmic web, the vast network of filaments and voids that make up the large-scale structure of the universe. Dark energy, with its repulsive force, acts as a cosmic sculptor, determining how matter is distributed across this web. In the early universe, gravity was the dominant force, pulling matter together to form the first galaxies and clusters. But as the universe expanded, dark energy began to take over, counteracting gravity's pull and driving the accelerated expansion we see today. This shift didn't just affect the rate of expansion, it also influenced how galaxies formed and evolved. In regions where dark energy's influence was stronger, matter was pushed apart, creating vast cosmic voids. In areas where gravity still held sway, galaxies and clusters continued to grow, forming the dense nodes of the cosmic web. One striking example of dark energy's impact can be seen in the distribution of galaxy clusters. These massive structures, containing hundreds or even thousands of galaxies, are not randomly scattered across the universe. Instead, they align along the filaments of the cosmic web, with dark energy shaping the spaces between them. Over billions of years, dark energy has stretched these filaments, creating the intricate patterns we observe today. Without dark energy, the universe would look very different. Galaxies would be more tightly packed, and the cosmic web would lack the vast voids that define its structure. But dark energy's role doesn't stop there. It also affects the evolution of individual galaxies. As the universe expands, dark energy pushes galaxies apart, reducing the likelihood of collisions and mergers. This means that galaxies in a dark energy-dominated universe are less likely to grow through interactions with their neighbors. Instead, they evolve more independently, with their growth driven by internal processes like star formation and the accretion of gas. This has profound implications for the diversity of galaxies we see today, from spiral galaxies like our Milky Way to massive elliptical galaxies found at the centers of clusters. The interplay between dark energy and galaxy formation is a reminder of how interconnected the cosmos truly is. From the largest structures in the universe to the individual galaxies within them, dark energy leaves its mark, shaping the universe on every scale. As we continue to study these phenomena, we gain not only a deeper understanding of dark energy, but also a clearer picture of how the universe came to be the way it is. And with each discovery, we move closer to unraveling one of the greatest mysteries of the cosmic dark energy era. Now shifting our focus to one of the most perplexing puzzles in modern physics, we encounter the vacuum energy paradox. At its core, this mystery revolves around the concept of vacuum energy, a form of energy that exists even in the emptiest regions of space. According to quantum mechanics, empty space isn't truly empty. Instead, it's a seething, dynamic arena where particles and antiparticles constantly pop in and out of existence. This quantum activity gives rise to vacuum energy, a theoretical energy that permeates the fabric of the universe. Here's where things get puzzling. When scientists calculate the predicted value of vacuum energy using quantum field theory, the result is staggeringly large, so large, in fact, that it should cause the universe to expand at an unimaginable rate. But when we compare this prediction to the observed value of dark energy, which drives the universe's accelerated expansion, the numbers don't match. The observed value of dark energy is incredibly tiny, more than 120 orders of magnitude smaller than the predicted value of vacuum energy. This enormous discrepancy is what we call the vacuum energy paradox, and it remains one of the most baffling unsolved problems in physics. Why does this matter? Because vacuum energy is one of the leading candidates for explaining dark energy. If the two are connected, understanding this paradox could unlock the secrets of dark energy and, by extension, the fate of the universe. But the gap between theory and observation is so vast that it suggests our current understanding of physics is incomplete. Some scientists propose that unknown mechanisms might be cancelling out most of the vacuum energy, leaving behind the small amount we observe as dark energy. Others suggest that our theories of quantum mechanics and gravity need to be fundamentally revised to resolve this inconsistency. The vacuum energy paradox isn't just a technical problem, it's a profound challenge to our understanding of the universe. It forces us to question the very foundations of physics and consider whether we're missing a crucial piece of the cosmic puzzle. As researchers continue to explore this mystery, they're not only searching for answers about dark energy, but also pushing the boundaries of human knowledge. And in doing so, they remind us that the universe is far stranger and more mysterious than we ever imagined. Now, as we venture deeper into the enigmatic realm of dark energy, we encounter a concept that sounds like it's straight out of a science fiction novel, phantom energy. This hypothetical form of dark energy is not just mysterious, it's downright unsettling. Unlike the more familiar forms of dark energy that drive the universe's accelerated expansion, phantom energy has a unique and dramatic twist. It suggests that dark energy's influence could grow stronger over time, eventually tearing the very fabric of the cosmos apart in an event known as the Big Rip. Imagine this: as phantom energy accumulates, it doesn't just push galaxies apart, it could stretch and shred everything in its path. Stars, planets, even atoms themselves could be ripped apart in a catastrophic finale. This isn't just a distant possibility. It's a scenario that could unfold over billions of years, but the implications are so profound that they've captured the imagination of scientists and science enthusiasts alike. The Big Rip isn't just an end to the universe as we know it, it's a complete unraveling of reality itself. What makes phantom energy so fascinating is its potential to challenge our understanding of the universe's ultimate fate. While other theories, like the Big Freeze or Big Crunch, offer more gradual or cyclical endings, the Big Rip is abrupt and violent. It raises questions about the nature of dark energy itself. Could it really behave in such an extreme way? And if so, what does that mean for the laws of physics as we understand them? These questions don't just keep scientists up at night, they push the boundaries of what we think is possible. But phantom energy isn't just a theoretical curiosity, it's also a source of deep concern. If the universe is indeed headed toward a Big Rip, it would mean that the forces driving its expansion are far more powerful and far more destructive than we've ever imagined. This idea forces us to confront the fragility of existence on a cosmic scale. It's a reminder that the universe, for all its beauty and complexity, is governed by forces that are still largely beyond our comprehension. As researchers continue to explore the phantom energy hypothesis, they're not just probing the limits of theoretical physics, they're also grappling with questions that touch on the very nature of reality. What does it mean for the universe to end in such a dramatic way? And what can we learn about dark energy by studying its most extreme possibilities? These are the kinds of questions that make phantom energy both a terrifying and thrilling area of study, one that keeps us looking to the stars with a mix of awe and apprehension. Now, as we shift our focus to another intriguing mystery, let's explore the fascinating connection between dark energy and time itself. Could dark energy, the force driving the universe's expansion, also be shaping the very fabric of time? This idea might sound like something out of a science fiction story, but it's a serious topic of discussion among cosmologists and physicists. One theory suggests that dark energy might influence the flow of time, acting as a kind of cosmic clock that determines how fast or slow time moves on a universal scale. Imagine time as a river flowing steadily forward. Dark energy could be like the current, subtly guiding the river's pace. In regions where dark energy is more dominant, time might flow differently compared to areas where its influence is weaker. This could mean that time itself isn't constant across the universe, a mind-bending concept that challenges our everyday understanding of how time works. Another idea takes this even further, proposing that dark energy could be a manifestation of what physicists call the arrow of time. The arrow of time is the one-way direction in which time flows from the past to the future. It's why we remember yesterday but not tomorrow. Some scientists speculate that dark energy might be tied to this unidirectional flow, acting as the engine that keeps time moving forward. Without dark energy, the arrow of time might not exist as we know it, and the universe could behave in ways that are completely alien to our experience. To make this complex idea more relatable, think of dark energy as the wind pushing a sailboat across the ocean. Just as the wind determines the boat's speed and direction, dark energy could be shaping how time progresses across the cosmos. If the wind changes, the boat's journey changes too. Similarly, if dark energy's influence shifts, the flow of time might also change in ways we can't yet fully predict. These theories open up a world of possibilities, raising questions about the fundamental nature of time and its relationship to the universe's expansion. Could dark energy be the key to understanding why time moves forward? And if so, what does that mean for the future of the cosmos? These are the kinds of questions that keep scientists exploring the mysteries of dark energy, searching for answers that could reshape our understanding of reality itself. As we continue to unravel these cosmic puzzles, one thing is clear. Dark energy isn't just shaping the universe, it might also be shaping the very essence of time. And that's a mystery worth exploring further. Now, as we turn our attention to another cosmic puzzle, let's dive into the missing mass problem and its intricate relationship with dark energy. While dark energy is driving the universe's accelerated expansion, there's another mysterious player in the cosmic game: dark matter. Together, these two invisible forces shape the universe on the largest scales, but their interactions with ordinary matter, the stuff we can see, remain one of the most perplexing challenges in modern cosmology. The missing mass problem arises because the amount of matter we observe in the universe, stars, galaxies, gas, and dust, simply doesn't add up to what's needed to explain the gravitational effects we see. For example, galaxies rotate faster than they should if only the visible matter were holding them together. This discrepancy led scientists to propose the existence of dark matter, an invisible substance that doesn't emit light but exerts a gravitational pull. Yet, even with dark matter in the equation, there's still a gap when we factor in the influence of dark energy. Dark energy, on the other hand, doesn't clump like matter. Instead, it permeates space uniformly, pushing galaxies apart and counteracting gravity's pull. This creates a cosmic tug-of-war. Dark matter tries to pull structures together, while dark energy works to push them apart. The challenge lies in understanding how these two forces interact with ordinary matter and each other. Why does dark energy dominate on large scales, while dark matter seems to govern the behavior of galaxies and galaxy clusters? And how do these interactions shape the distribution of mass we observe across the universe? One of the biggest hurdles is that dark energy and dark matter are fundamentally different in nature. Dark matter behaves like a particle, clumping together to form the scaffolding for galaxies and cosmic structures. Dark energy, however, is more like a property of space itself, stretching the universe apart. Reconciling these two forces requires a deeper understanding of their origins and how they influence the cosmos over time. Ongoing research is tackling this mystery from multiple angles. Scientists are using advanced telescopes and simulations to map the distribution of matter in the universe, searching for clues about how dark energy and dark matter interact. Projects like the Dark Energy Survey and the upcoming Vera-C Rubin Observatory aim to measure the effects of dark energy on the large-scale structure of the cosmos with unprecedented precision. Meanwhile, particle physicists are hunting for dark matter particles in underground experiments. hoping to shed light on its properties and how it might connect to dark energy. The missing mass problem isn't just a scientific curiosity, it's a key piece of the puzzle in understanding the universe's past, present, and future. By unraveling how dark energy, dark matter, and ordinary matter interact, we might finally uncover the secrets of the cosmos's hidden architecture. And as we continue to explore, one thing is certain: the answers we find could reshape our understanding of reality itself. With this mystery still unfolding, let's move forward to explore another fascinating aspect of dark energy, its potential role in the early universe. Now, as we shift our gaze to the earliest moments of the universe, let's explore the intriguing possibility that dark energy might have played a role in cosmic inflation. This period, just fractions of a second after the Big Bang, saw the universe expand at an unimaginable rate, stretching from a tiny speck to something far larger than the observable universe we see today. But what powered this rapid expansion, and could dark energy, the force driving the universe's accelerated expansion today, be connected to this ancient event? Cosmic inflation is one of the most widely accepted theories in cosmology, explaining why the universe appears so uniform on large scales and why tiny quantum fluctuations grew into the vast structures we see today. But the mechanism behind inflation remains a mystery. Some scientists speculate that dark energy, or something like it, might have been the driving force behind this explosive growth. If true, this would mean that dark energy isn't just a modern phenomenon, it could have been shaping the universe since its very beginning. One idea is that dark energy is a remnant of inflation, a leftover energy field that persisted after the inflationary period ended. In this scenario, the same force that caused the universe to expand rapidly in its infancy might still be at work today, albeit in a much weaker form. This would suggest a deep connection between the early universe and the cosmic dark energy era we're living in now. However, not all scientists agree. Some argue that dark energy and inflation are entirely separate phenomena, driven by different mechanisms and operating on different scales. The challenge lies in finding evidence to support either theory. Inflation left behind subtle imprints in the cosmic microwave background, the afterglow of the Big Bang, but detecting a direct link to dark energy is far more difficult. If dark energy is indeed a remnant of inflation, it would mean that the universe's expansion has been influenced by the same fundamental force for billions of years. On the other hand, if dark energy is unrelated, it raises even more questions about its origins and why it dominates the universe today. As researchers continue to probe the mysteries of the early universe, they're using advanced tools like the James Webb Space Telescope and next-generation cosmic microwave background experiments to search for clues. By studying the faint echoes of inflation and the effects of dark energy on the universe's large-scale structure, they hope to uncover whether these two phenomena are connected or if they represent entirely different chapters in the cosmic story. The role of dark energy in cosmic inflation is more than just a scientific curiosity. It's a window into the universe's deepest secrets. Whether it's a remnant of the Big Bang or a completely separate force, understanding this connection could revolutionize our knowledge of the cosmos. And as we continue to explore, we're reminded that the universe's greatest mysteries often lie in its earliest moments. With this cosmic puzzle still unfolding, let's turn our attention to another fascinating question: how dark energy might be connected to the anthropic principle and the conditions necessary for life in the universe. Now, as we venture into the realm of the anthropic principle, we find ourselves grappling with one of the most profound questions in cosmology. Why does dark energy have the precise value it does, and could this value be fine-tuned to allow for the existence of life? This idea, known as the anthropic principle, suggests that the fundamental constants of the universe, including dark energy, are set in such a way that they make life possible. But is this just a cosmic coincidence, or is there something deeper at play? the anthropic principle comes in two main forms, the weak and the strong. The weak anthropic principle simply states that the conditions we observe in the universe must be compatible with the existence of observers, us. In other words, we wouldn't be here to ask these questions if the universe weren't structured in a way that allows for life. The strong anthropic principle, on the other hand, goes a step further, suggesting that the universe must have properties that allow life to develop at some point in its history. When applied to dark energy, this principle raises the question, why is dark energy's density so small yet not zero? If it were much larger, the universe would have expanded too quickly for galaxies, stars, and planets to form. If it were much smaller, gravity might have caused the universe to collapse back on itself long before life could emerge. This fine-tuning of dark energy has sparked intense debate among scientists and philosophers. Some argue that it points to the existence of a multiverse, a vast collection of universes, each with different physical constants. In this scenario, we happen to live in a universe where dark energy's value is just right for life to exist. Others see it as evidence of a deeper, yet to be discovered law of physics that dictates the value of dark energy. And then there are those who view it as a purely random occurrence, a lucky roll of the cosmic dice. The implications of the anthropic principle extend far beyond dark energy. If the universe is fine-tuned for life, it challenges our understanding of the cosmos and our place within it. It forces us to confront questions about the nature of reality, the possibility of other universes, and even the existence of a higher purpose or design. At the same time, it raises practical questions for cosmology. How can we test these ideas, and what would it mean for our understanding of the universe if the anthropic principle were proven true? As we continue to explore the mysteries of dark energy, the anthropic principle serves as a reminder that the universe is not just a collection of random events, but a finely balanced system that allows for the emergence of complexity and life. Whether this balance is the result of chance, necessity, or something beyond our current understanding, it remains one of the most captivating questions in science. And as we ponder this cosmic puzzle, we're reminded that the search for answers is as much about understanding ourselves as it is about understanding the universe. With this thought-provoking concept in mind, let's turn our attention to the next mystery: the search for dark energy probes and the cutting-edge tools scientists are using to unravel its secrets. Now, as we shift our focus to the tools and techniques scientists are using to uncover the secrets of dark energy, we enter a realm where cutting-edge technology meets cosmic curiosity. The search for dark energy probes is a fascinating journey, one that relies on a variety of methods to observe and measure the invisible force shaping our universe. Among these, three stand out as particularly powerful: supernova, baryon acoustic oscillations, and weak gravitational lensing. Supernova, the explosive deaths of massive stars, have been instrumental in our understanding of dark energy. By observing these cosmic fireworks, scientists can measure distances across the universe with remarkable precision. It was through studying distant supernova in the late 1990s that researchers first discovered the universe's accelerating expansion, a breakthrough that earned them the Nobel Prize. Today, supernova continue to serve as cosmic mile markers, helping us map the universe's expansion over time and providing critical clues about dark energy's influence. Another key method is the study of baryon acoustic oscillations, or BAO. These are subtle ripples in the distribution of galaxies, remnants of sound waves that traveled through the early universe. By measuring the spacing of these ripples, scientists can trace the universe's expansion history and infer the effects of dark energy. Think of BAOs as cosmic fingerprints, unique patterns left behind by the universe's infancy that help us understand its growth and evolution. Weak gravitational lensing, on the other hand, offers a different perspective. This phenomenon occurs when the gravity of massive objects, like galaxy clusters, bends the light from more distant objects. By studying how dark energy affects the distribution of matter in the universe, weak lensing allows scientists to map the cosmic web and measure the growth of large-scale structures over time. It's like using a cosmic magnifying glass to peer into the hidden architecture of the universe. But the search for dark energy doesn't stop there. Exciting new missions and experiments are on the horizon, each designed to push the boundaries of our knowledge. One such mission is the European Space Agency's Euclid telescope, set to launch in the coming years. Euclid will map billions of galaxies using both weak lensing and BAOs to create a detailed picture of dark energy's impact on the universe. Similarly, NASA's Nancy Grace Roman Space Telescope, scheduled for launch later this decade, will study supernova and weak lensing on an unprecedented scale, offering new insights into the nature of dark energy. On the ground, projects like the Dark Energy Survey and the upcoming Vera-C Rubin Observatory are using powerful telescopes to observe vast swaths of the sky, collecting data that will help refine our understanding of dark energy. These efforts, combined with advancements in theoretical modeling and computational power, are bringing us closer than ever to unraveling this cosmic mystery. As we look to the future, the search for dark energy probes reminds us that science is a collaborative endeavor, one that spans continents, disciplines, and generations. Each observation, each experiment, brings us one step closer to understanding the invisible force that shapes our universe. And as we continue to explore, we're reminded that the answers we seek may lie not just in the stars, but in the very fabric of space and time itself. With these groundbreaking tools and missions in mind, let's now turn our attention to the next mystery, the role of quantum mechanics in dark energy, and how the smallest scales of the universe might hold the key to understanding its largest mysteries. Now, as we venture into the realm of the infinitesimally small, we find ourselves face to face with one of the most profound mysteries of the cosmos, the role of quantum mechanics in dark energy. At the heart of this mystery lies a fundamental question: how do the rules governing the smallest particles in the universe connect to the vast, invisible force shaping its expansion? To understand this, we must first explore the strange and counterintuitive world of quantum mechanics, where particles can exist in multiple states at once, and empty space is anything but empty. Quantum mechanics tells us that even in a vacuum, space is teeming with activity. Virtual particles pop in and out of existence, creating a sea of energy known as vacuum energy. This energy is thought to be a potential candidate for dark energy, but here's the catch. When scientists calculate the expected value of vacuum energy using quantum theory, the result is staggeringly larger than the observed value of dark energy. This discrepancy, known as the vacuum energy paradox, is one of the biggest unsolved problems in physics. It suggests that either our understanding of quantum mechanics is incomplete, or there's something fundamental about dark energy that we're missing. Adding to the complexity is the challenge of reconciling quantum mechanics with general relativity, Einstein's theory of gravity. While quantum mechanics excels at describing the behavior of particles on the smallest scales, general relativity governs the large-scale structure of the universe. These two frameworks, however, don't play well together. When scientists try to combine them to explain dark energy, the math breaks down, leading to contradictions and infinities. This tension between the two theories has fueled decades of research, with physicists searching for a unified theory that can bridge the gap between the quantum and cosmic realms. One promising avenue is the idea that dark energy might be linked to quantum fields, invisible forces that permeate the universe and dictate the behavior of particles. Some theories suggest that dark energy could be the result of a new, undiscovered quantum field, one that interacts with gravity in a way we don't yet understand. Others propose that dark energy might emerge from the collective behavior of countless quantum particles, creating an effect that only becomes noticeable on cosmic scales. While these ideas are still speculative, they highlight the potential for quantum mechanics to unlock the secrets of dark energy. Yet, the challenges remain immense. Detecting quantum effects on the scale of the entire universe is no small feat, and our current tools and technologies are only beginning to scratch the surface. Experiments like those conducted at the Large Hadron Collider aim to probe the quantum realm for clues, while theoretical physicists work tirelessly to develop new models that can reconcile quantum mechanics with the observed behavior of dark energy. It's a race against time and complexity, but one that holds the promise of revolutionizing our understanding of the universe. As we delve deeper into the quantum world, we're reminded that the answers to some of the universe's biggest questions may lie in its smallest details. The interplay between quantum mechanics and dark energy is a frontier of modern science, one that challenges our assumptions and pushes the boundaries of human knowledge. And as we continue to explore, we may find that the key to understanding dark energy, and perhaps the universe itself, lies in the delicate dance of particles and fields that define the quantum realm. With this in mind, let's now turn our attention to the next mystery, the holographic principle and its potential connection to dark energy, a theory that suggests the universe might be a projection of information encoded on a boundary surface. Now, as we step into the realm of the holographic principle, we find ourselves exploring one of the most mind-bending ideas in modern physics, a theory that suggests our universe might be a projection like a cosmic hologram. At its core, the holographic principle proposes that all the information contained within a volume of space can be thought of as encoded on a boundary surface surrounding that space. Imagine the universe as a giant movie screen, with everything we see, touch, and experience being a projection from the data stored on its edges. This radical idea challenges our traditional understanding of space and reality, and it might just hold the key to unraveling the mystery of dark energy. The holographic principle emerged from the study of black holes, where physicists discovered that the information about everything swallowed by a black hole could be encoded on its event horizon, the boundary beyond which nothing can escape. This led to the startling realization that the universe itself might operate in a similar way, with all the information about its contents encoded on a vast, invisible surface. If this is true, then dark energy, the force driving the universe's accelerated expansion, could be deeply connected to this holographic framework. Some scientists speculate that dark energy might arise from the way information is processed or projected across this cosmic boundary, creating an effect that we perceive as the expansion of space. But how does this connect to dark energy? One possibility is that dark energy is a manifestation of the way information is distributed and processed on this boundary surface. Just as a hologram creates a three-dimensional image from a two-dimensional surface, the universe's expansion might be a result of the way information is projected from its edges. This could explain why dark energy appears to be a property of space itself, rather than something tied to matter or energy within it. It's a theory that blurs the line between the physical and the informational, suggesting that the very fabric of reality might be more like a cosmic code than a collection of particles and forces. The implications of this idea are profound. If the holographic principle is correct, it could revolutionize our understanding of not just dark energy, but the nature of reality itself. It would mean that the universe is fundamentally informational, with everything we observe being a projection of data encoded on its boundaries. This perspective could also help resolve some of the contradictions between quantum mechanics and general relativity, offering a unified framework that bridges the gap between the smallest particles and the largest structures in the cosmos. Of course, the holographic principle is still a speculative idea, and much work remains to be done to test its validity. Experiments and observations, such as those studying the cosmic microwave background or the behavior of black holes, could provide clues about whether our universe truly operates like a hologram. Theoretical physicists are also exploring mathematical models that could explain how dark energy fits into this framework, pushing the boundaries of our understanding. As we ponder the holographic principle, we're reminded that the universe is far stranger and more interconnected than we often imagine. The idea that everything we see might be a projection from a hidden boundary challenges our assumptions and invites us to think in entirely new ways. And as we continue to explore this frontier, we may find that the key to understanding dark energy, and perhaps the universe itself, lies not in the stars or the particles, but in the information that shapes the very fabric of reality. With this in mind, let's now turn our attention to the next mystery, the role of dark energy in black hole dynamics, where the invisible force shaping the cosmos might also influence the behavior of these enigmatic objects. Now, as we shift our focus to the mysterious interplay between dark energy and black holes, we enter a realm where the invisible force shaping the cosmos might also dictate the fate of these enigmatic objects. Black holes, often thought of as the ultimate cosmic vacuum cleaners, are regions of space where gravity is so intense that nothing, not even light, can escape. But what happens when dark energy, the force driving the universe's accelerated expansion, enters the picture? Could it influence how black holes grow, evolve, or even fade away over time? One intriguing possibility is that dark energy might affect the rate at which black holes grow. As the universe expands, dark energy pushes galaxies and matter apart, potentially altering the flow of material into black holes. Imagine a black hole at the center of a galaxy, feeding on stars and gas. If dark energy causes the surrounding matter to spread out more rapidly, the black hole might find itself with less food to consume, slowing its growth over cosmic timescales. This could mean that black holes in a dark energy-dominated universe might not grow as large or as quickly as they would in a universe without this mysterious force. But dark energy's influence might not stop there. Some theories suggest that it could also play a role in the evaporation of black holes. According to Stephen Hawking's groundbreaking work, black holes aren't entirely black. They emit a faint radiation known as Hawking radiation, causing them to lose mass and eventually evaporate over unimaginably long periods. Dark energy, with its ability to stretch space itself, might accelerate this process. If space expands faster due to dark energy, the rate at which black holes lose mass through Hawking radiation could increase, potentially shortening their lifespan. This raises fascinating questions about the ultimate fate of black holes in a universe dominated by dark energy. Another angle to consider is how dark energy might influence the behavior of supermassive black holes, which reside at the centers of galaxies. These colossal objects are thought to play a crucial role in shaping their host galaxies, but if dark energy alters the distribution of matter on large scales, it could also impact how these black holes interact with their surroundings. For instance, dark energy might affect the formation of galactic structures, such as spiral arms or clusters, which in turn could influence how supermassive black holes grow and evolve. This interplay between dark energy and black holes could be a key piece of the puzzle in understanding the large-scale structure of the universe. Of course, these ideas are still largely theoretical, and much remains to be explored. Observational evidence is scarce, and the effects of dark energy on black holes are subtle, playing out over billions of years. However, advancements in technology, such as more sensitive telescopes and gravitational wave detectors, could provide new insights into this cosmic dance. By studying the behavior of black holes in different regions of the universe, scientists might uncover clues about how dark energy shapes their dynamics. As we delve deeper into this mystery, we're reminded once again of the profound interconnectedness of the cosmos. Dark energy, black holes, and the fabric of space-time are all part of a grand cosmic tapestry, each influencing the other in ways we're only beginning to understand. The role of dark energy in black hole dynamics is just one piece of this puzzle, but it's a piece that could help us unlock some of the universe's deepest secrets. With this in mind, let's now turn our attention to the next mystery, the cosmic coincidence problem, where the puzzling balance between dark energy and matter in the universe raises questions about the very nature of our existence. Now, as we step into the next chapter of our cosmic exploration, we encounter one of the most perplexing mysteries of all, the cosmic coincidence problem. Why is it that the density of dark energy in the universe today is so strikingly similar to the density of matter? This balance seems almost too perfect to be random, and it raises profound questions about the nature of our universe. To understand why this is so puzzling, let's take a step back. Dark energy, as we've discussed, is the mysterious force driving the accelerated expansion of the universe. Matter, on the other hand, includes everything we can see: stars, planets, galaxies, and even the invisible dark matter that makes up a significant portion of the cosmos. These two components, dark energy and matter, are fundamentally different in how they behave. Matter clumps together under gravity, forming structures like galaxies and clusters, while dark energy acts as a repulsive force, pushing everything apart. The strange part is that, despite their opposing roles, their densities are almost equal in the present-day universe. This balance is not something that was expected. In fact, as the universe expands, the density of matter decreases because it becomes more spread out. Dark energy, however, behaves differently. Its density remains constant over time. This means that in the past, matter was far more dominant, and in the distant future, dark energy will overwhelmingly dominate. The fact that we happen to live in an era where their densities are so close is what makes this a cosmic coincidence. So, why does this matter? For one, it challenges our understanding of the universe's evolution. If dark energy's density were even slightly different, the universe as we know it might not exist. A stronger dark energy would have caused the universe to expand so rapidly that galaxies and stars might never have formed. A weaker dark energy, on the other hand, might have allowed gravity to pull everything back together, leading to a cosmic collapse. The fact that we're in this Goldilocks zone, where the densities are just right for life to exist, is both fascinating and deeply mysterious. This coincidence has led some scientists to wonder if there's a deeper principle at work. Could it be that dark energy and matter are somehow connected in a way we don't yet understand? Or is this balance a result of some fundamental law of physics that we've yet to uncover? Some have even suggested that this might be a clue pointing toward the existence of a multiverse, a vast collection of universes, each with different properties. In such a scenario, we might simply live in one of the rare universes where the conditions are just right for life to thrive. Others argue that this coincidence might be a sign that our understanding of dark energy is incomplete. Perhaps dark energy isn't a constant force but something that changes over time, interacting with matter in ways we haven't yet detected. This idea opens up exciting possibilities for new physics, challenging us to rethink our models of the cosmos. As we ponder these questions, we're reminded once again of how much we still have to learn about the universe. The cosmic coincidence problem isn't just a curiosity, it's a window into some of the deepest mysteries of existence. What does this balance tell us about the nature of dark energy? Could it hold the key to understanding the ultimate fate of the universe? These are the questions that drive scientists to keep exploring, pushing the boundaries of our knowledge. With this mystery in mind, let's now turn our attention to the next intriguing puzzle: the role of dark energy in shaping the vast, empty regions of space known as cosmic voids, and how these voids might hold clues to the universe's large-scale structure. Now, as we shift our gaze to the vast, empty expanses of the cosmos, we encounter another fascinating mystery: the role of dark energy in shaping cosmic voids. These voids are the universe's great empty spaces, regions where matter is sparse and galaxies are few and far between. But don't let their emptiness fool you. These voids are far from insignificant. In fact, they play a crucial role in helping us understand the large-scale structure of the universe and the influence of dark energy. To grasp the importance of cosmic voids, let's start with a simple question: what exactly are they? Imagine the universe as a cosmic web, a vast network of filaments made up of galaxies, gas, and dark matter. These filaments stretch across the cosmos, connecting clusters of galaxies like threads in a tapestry. But between these threads lie the voids, enormous regions where the density of matter is much lower than average. Some of these voids can span hundreds of millions of light years, making them some of the largest structures in the universe. So, how does dark energy come into play? Dark energy, as we've discussed, is the force driving the accelerated expansion of the universe. This expansion doesn't just affect galaxies and clusters, it also influences the growth and evolution of cosmic voids. As dark energy pushes the universe apart, it causes these voids to grow larger over time. In fact, the expansion of voids is one of the key ways scientists study the effects of dark energy on the cosmos. But why are voids so important for understanding dark energy? For one, they act as natural laboratories for testing our theories about the universe's expansion. Because voids contain so little matter, they are less affected by the gravitational pull of galaxies and clusters. This makes them ideal places to observe the influence of dark energy in its purest form. By studying how voids expand and evolve, scientists can gain valuable insights into the properties of dark energy and how it shapes the universe on the largest scales. Another reason voids are so intriguing is their connection to the cosmic web. The distribution of matter in the universe isn't random, it follows a pattern shaped by the interplay of gravity and dark energy. Voids are the flip side of this pattern, the empty spaces that define the boundaries of the cosmic web. By mapping the distribution of voids, scientists can better understand how dark energy influences the formation and evolution of the universe's large-scale structure. Interestingly, voids also provide clues about the early universe. The seeds of cosmic voids were planted during the inflationary period, just moments after the Big Bang. Tiny fluctuations in the density of matter grew over billions of years, eventually giving rise to the voids we see today. By studying these voids, scientists can learn more about the conditions of the early universe and how dark energy has shaped its evolution over time. As we explore the mysteries of cosmic voids, we're reminded once again of the profound influence dark energy has on the cosmos. These vast, empty regions are not just gaps in the universe, they are windows into the forces that shape it. By studying voids, we can uncover new insights into the nature of dark energy and its role in the universe's past, present, and future. With this in mind, let's now turn our attention to the next intriguing puzzle: the connection between dark energy and gravity, and how alternative theories of gravity might help us better understand the universe's expansion. Now, as we venture deeper into the mysteries of dark energy, we arrive at a question that challenges the very foundations of our understanding. Could dark energy be a manifestation of gravity itself? This idea might sound counterintuitive at first, but it's a possibility that has sparked intense debate among scientists. To explore this, we need to revisit one of the most fundamental forces in the universe, gravity, and consider how it might behave differently on cosmic scales. At the heart of this mystery is the fact that dark energy seems to act in direct opposition to gravity. While gravity pulls matter together, dark energy pushes it apart, driving the accelerated expansion of the universe. But what if this apparent opposition is just a misunderstanding? What if dark energy isn't a separate force at all, but rather a different expression of gravity? This is where alternative theories of gravity come into play. One such theory is known as FR gravity. In simple terms, FR gravity proposes that the equations governing gravity, as described by Einstein's general relativity, might need to be modified on the largest scales. Instead of gravity being a fixed, unchanging force, FR gravity suggests that it could vary depending on the curvature of spacetime. This variation could potentially explain the effects we currently attribute to dark energy, such as the accelerated expansion of the universe. The appeal of FR gravity lies in its ability to unify two seemingly unrelated phenomena, gravity and dark energy, under a single framework. By tweaking the equations of general relativity, this theory offers a way to account for the universe's expansion without invoking an entirely new form of energy. Instead, it suggests that our understanding of gravity might simply be incomplete, especially when applied to the vast cosmic scales where dark energy's effects are most pronounced. But FR gravity isn't the only alternative theory out there. Other models, such as scalar tensor theories and brane-world scenarios, also propose modifications to gravity that could explain the universe's accelerated expansion. These theories often introduce new fields or dimensions, adding layers of complexity to our understanding of the cosmos. While they differ in their specifics, they all share a common goal: to reconcile the observed behavior of the universe with a more comprehensive theory of gravity. Of course, these alternative theories aren't without their challenges. One of the biggest hurdles is testing them against observations. While general relativity has been incredibly successful in explaining phenomena like the orbit of Mercury and the bending of light around massive objects, modified gravity theories must also account for these successes while explaining the effects of dark energy. This requires precise measurements and observations, often at the very limits of our current technology. Despite these challenges, the search for a deeper understanding of gravity and dark energy continues. Whether dark energy is a separate entity or a manifestation of modified gravity, the implications are profound. It could reshape our understanding of the universe's past, present, and future, offering new insights into the forces that govern its evolution. As we ponder this connection between dark energy and gravity, we're reminded once again of the complexity and beauty of the cosmos. The universe is full of mysteries, and each one invites us to question, explore, and discover. With this in mind, let's now turn our attention to the next intriguing puzzle: the role of dark energy in the early universe and how it might have influenced the conditions during the Big Bang. Now, as we shift our gaze to the very beginnings of the cosmos, we find ourselves asking, could dark energy have played a role in the universe's earliest moments? This question takes us back to the Big Bang, the explosive event that set the stage for everything we see today. While dark energy is often associated with the universe's current accelerated expansion, some scientists believe it might have been at work even in those first fleeting seconds. To understand this possibility, we need to revisit the conditions of the early universe. In the moments following the Big Bang, the universe was unimaginably hot and dense, filled with a seething plasma of particles and energy. It was during this time that the seeds of all cosmic structures, galaxies, stars, and even the cosmic web were planted. But what if dark energy was also present, subtly shaping these early conditions? One intriguing theory suggests that dark energy might have influenced the rate of the universe's initial expansion. While inflation, a period of rapid expansion in the early universe, is well supported by evidence, some researchers propose that dark energy could have played a complementary role. Instead of fading away after inflation, dark energy might have lingered, subtly affecting the universe's growth and setting the stage for its later accelerated expansion. Another idea is that dark energy could have interacted with other fundamental forces during the Big Bang. For instance, it might have influenced the balance between matter and antimatter, or even played a part in the formation of the first particles. These interactions, though subtle, could have had profound consequences for the universe's evolution, shaping the way matter clumped together to form galaxies and larger structures. However, studying dark energy's role in the early universe is no easy task. The extreme conditions of the Big Bang are difficult to replicate, even in the most advanced particle accelerators. Additionally, the evidence from that era is faint, preserved only in the faint echoes of the cosmic microwave background and the distribution of galaxies we observe today. Yet, these clues are invaluable, offering glimpses into a time when the universe was just beginning to take shape. As we piece together these fragments of the past, we're reminded of how interconnected the universe's history truly is. Dark energy, often seen as a modern mystery, might have roots that stretch back to the very beginning. Whether it acted as a subtle force during the Big Bang or emerged later to drive the universe's expansion, its influence is undeniable. And as we continue to explore these ideas, we inch closer to understanding not just the universe's present, but its origins as well. With this in mind, let's now turn our attention to another fascinating aspect of dark energy, its potential connection to cosmic symmetry breaking, and how it might have shaped the fundamental laws of the universe. Now, as we delve into the intricate dance of cosmic forces, let's explore how dark energy might be intertwined with one of the most profound events in the universe's history, cosmic symmetry breaking. This phenomenon, which occurred in the earliest moments after the Big Bang, is thought to have shaped the fundamental laws of physics as we know them today. But could dark energy have played a role in this pivotal process? To understand this, we need to revisit the concept of symmetry breaking. In the early universe, the forces of nature, gravity, electromagnetism, and the strong and weak nuclear forces were unified into a single symmetrical force. As the universe expanded and cooled, this symmetry began to break, giving rise to the distinct forces we observe today. This process is akin to water freezing into ice. While liquid water is uniform and symmetrical, ice forms unique, asymmetrical structures. Similarly, the breaking of cosmic symmetries led to the diversity of particles and forces that make up our universe. Now, here's where dark energy enters the picture. Some theories suggest that dark energy might have influenced the way these symmetries broke. For instance, if dark energy was present in the early universe, it could have subtly altered the conditions under which symmetry breaking occurred. This might explain why certain particles, like quarks and electrons, have the masses and properties they do. In other words, dark energy could have been a hidden hand guiding the universe toward its current state. Another intriguing possibility is that dark energy itself is a remnant of symmetry breaking. Just as the Higgs field gives particles their mass through a process called spontaneous symmetry breaking, dark energy might be the result of a similar mechanism. This would mean that dark energy isn't just a mysterious force driving the universe's expansion. It could be a fundamental aspect of the cosmos, deeply connected to the very fabric of reality. The implications of this idea are staggering. If dark energy is linked to symmetry breaking, it could provide a bridge between particle physics and cosmology, two fields that often seem worlds apart. For particle physicists, this could offer new insights into the behavior of fundamental particles and forces. For cosmologists, it might shed light on the nature of dark energy itself, helping us understand why it behaves the way it does. However, unraveling this mystery is no small feat. The conditions of the early universe are difficult to replicate, and the evidence for dark energy's role in symmetry breaking is indirect at best. Yet, scientists are making progress. By studying the cosmic microwave background and the distribution of galaxies, they hope to uncover clues about how dark energy might have influenced the universe's formative moments. As we piece together these clues, we're reminded of how interconnected the cosmos truly is. Dark energy, often seen as a modern enigma, might have roots that stretch back to the very dawn of time. Whether it shaped the breaking of symmetries or emerged as a consequence of them, its influence is undeniable. And as we continue to explore these ideas, we inch closer to understanding not just the universe's present, but its deepest origins as well. With this in mind, let's now turn our attention to another fascinating aspect of dark energy, its role in the formation of cosmic filaments, the vast threads of matter that weave the cosmic web together. Now, as we shift our gaze to the grand tapestry of the universe, let's explore how dark energy plays a crucial role in shaping one of its most striking features, the cosmic filaments. These vast, thread-like structures form the backbone of the cosmic web, connecting galaxies and clusters across unimaginable distances. But how does dark energy, this mysterious force driving the universe's expansion, influence the formation of these intricate filaments? To understand this, we need to look at the cosmic web as a whole. Picture the universe as a vast network, with galaxies and clusters of galaxies strung along filaments like beads on a string. These filaments are not random. They are the result of a delicate balance between dark energy, dark matter, and ordinary matter. Dark matter, which makes up about 27% of the universe, acts as the scaffolding, providing the gravitational pull that draws matter together. Ordinary matter, the stuff we can see, stars, planets, and gas, follows this gravitational blueprint, clumping along the dark matter's invisible framework. But where does dark energy come in? While dark matter pulls matter together, dark energy pushes the universe apart, accelerating its expansion. This push and pull creates a dynamic interplay. As dark energy stretches the fabric of space, it influences how matter distributes itself over time. In the early universe, when dark energy's effects were less pronounced, matter could clump more easily, forming the seeds of filaments. Over billions of years, as dark energy's influence grew, it began to shape these filaments, stretching them into the vast, interconnected network we observe today. One fascinating aspect of this process is how dark energy affects the voids, the vast, empty regions between filaments. As dark energy accelerates the universe's expansion, it causes these voids to grow larger, pulling the filaments apart and stretching them even further. This creates a feedback loop. The larger the voids become, the more dark energy dominates and the more it shapes the filaments. It's a cosmic dance with dark energy leading the way. The interplay between dark energy, dark matter, and ordinary matter also determines the density and structure of the filaments themselves. In regions where dark matter is denser, filaments are thicker and more pronounced, hosting massive galaxy clusters. In less dense areas, filaments are thinner and more diffuse. Dark energy's influence ensures that this distribution is not static but evolves over time, shaping the cosmic web into its current form. Scientists study these filaments using advanced tools like galaxy surveys and computer simulations. By mapping the distribution of galaxies and measuring the effects of dark energy, they can piece together how these structures formed and evolved. For instance, the Sloan Digital Sky Survey has provided detailed maps of the cosmic web, revealing the intricate patterns of filaments and voids. These observations help us understand not just the universe's structure, but also the forces that shaped it. The role of dark energy in forming cosmic filaments is a reminder of how interconnected the universe truly is. From the smallest particles to the largest structures, everything is influenced by the same fundamental forces. As we continue to explore these filaments, we gain deeper insights into the nature of dark energy and its impact on the cosmos. And with each discovery, we come closer to unraveling the mysteries of the universe's grand design. With this understanding, let's now turn to another captivating aspect of dark energy: its potential influence on the life cycles of stars and the future of galaxies. Now, as we venture into the realm of stars and galaxies, let's uncover how dark energy might shape their evolution over unimaginable stretches of time. Stars, the brilliant beacons of the cosmos, are not immune to the subtle yet profound influence of dark energy. While their lives are governed by the balance of gravity and nuclear fusion, the accelerating expansion of the universe adds another layer of complexity to their existence. To understand this, let's start with the basics. Stars form when vast clouds of gas and dust collapse under their own gravity, igniting nuclear fusion in their cores. This process powers stars for billions of years, but their ultimate fate depends on their mass. Smaller stars, like our Sun, eventually exhaust their fuel and fade into white dwarfs, while more massive stars end in spectacular supernova, leaving behind neutron stars or black holes. But dark energy introduces a new variable into this cosmic equation. As dark energy accelerates the expansion of the universe, it affects the environment in which stars are born and evolve. Over cosmic timescales, the increasing distance between galaxies means that fewer gas clouds will collide and collapse to form new stars. This could lead to a gradual decline in star formation, a phenomenon astronomers refer to as cosmic starvation. In a universe dominated by dark energy, the raw materials for star formation, hydrogen and helium, become increasingly scattered, making it harder for new stars to ignite. But the influence of dark energy doesn't stop there. It also impacts the life cycles of existing stars. As the universe expands, galaxies are pulled farther apart and the gravitational bonds between them weaken. This could disrupt the delicate balance that allows stars to form and evolve within galaxies. Over time, galaxies may become more isolated with fewer interactions and mergers, which are key drivers of star formation. The result could be a universe where star formation slows to a crawl, and galaxies grow dimmer as their stellar populations age. One of the most intriguing implications of dark energy's influence is its effect on the ultimate fate of stars. In a universe where dark energy dominates, the expansion could stretch space so much that even the light from distant stars and galaxies would eventually be redshifted beyond detection. This would leave future civilizations, if they exist, with a night sky devoid of stars, a stark contrast to the vibrant cosmos we see today. Scientists are actively studying these possibilities using advanced simulations and observations. By modeling the effects of dark energy on star formation and galaxy evolution, they hope to predict how the universe will change over the next billions of years. For instance, the James Webb Space Telescope is providing unprecedented insights into the early stages of star formation, helping us understand how dark energy might alter these processes in the distant future. The role of dark energy in the evolution of stars is a reminder of how interconnected the cosmos truly is. From the birth of stars in dense gas clouds to their eventual demise, every stage of a star's life is influenced by the forces that shape the universe. As we continue to explore these mysteries, we gain a deeper appreciation for the delicate balance that governs the cosmos and the profound impact of dark energy on its future. With this in mind, let's now turn to another captivating question. How might dark energy influence the search for extraterrestrial life and the conditions necessary for its existence? Now, as we shift our gaze to the search for life beyond Earth, let's explore how dark energy might shape the conditions necessary for life to exist in the universe. The accelerating expansion driven by dark energy doesn't just affect galaxies and stars. It could also play a crucial role in determining where and how life might emerge. One of the key factors in the search for extraterrestrial life is the concept of habitability. For a planet to support life as we know it, it needs to be in the Goldilocks zone of its star, not too hot, not too cold, but just right for liquid water to exist. However, dark energy adds a new layer of complexity to this equation. As the universe expands, the distances between galaxies grow, and the availability of resources needed for life, such as hydrogen and other elements, becomes more scattered. Over time, this could make it increasingly difficult for planets to form in regions rich with the ingredients necessary for life. Moreover, dark energy's influence on the large-scale structure of the universe could affect the distribution of habitable planets. Galaxies in regions where dark energy's effects are more pronounced might become isolated, reducing the chances of interactions that could trigger star and planet formation. This means that, in the far future, the number of potentially habitable planets might decline as the universe continues to expand. But it's not just about the availability of resources. Dark energy could also impact the stability of planetary systems. As galaxies are pulled apart, the gravitational forces that hold star systems together might weaken, potentially destabilizing orbits and making it harder for life to thrive. Imagine a planet that once enjoyed a stable, life-friendly orbit suddenly being thrown into chaos as its star drifts farther from neighboring systems. Such disruptions could make the emergence and survival of life far more challenging. Another intriguing aspect is the role of dark energy in the evolution of intelligent civilizations. If life does exist elsewhere in the universe, the accelerating expansion could limit its ability to explore and communicate across vast cosmic distances. As galaxies move farther apart, the time and energy required for interstellar travel or communication could become prohibitive. This raises the question, could dark energy be a factor in why we haven't yet detected signs of advanced extraterrestrial civilizations? It's a thought-provoking possibility that adds another dimension to the Fermi paradox, the apparent contradiction between the high probability of extraterrestrial life and the lack of evidence for it. Scientists are also considering how dark energy might influence the conditions for life in the early universe. In the first few billion years after the Big Bang, dark energy's effects were minimal and the universe was more densely packed with matter. This period might have been more conducive to the formation of life-supporting planets, as resources were more abundant and interactions between galaxies were more frequent. Understanding this early era could provide clues about where to look for ancient civilizations or remnants of past life. As we continue to search for signs of life beyond Earth, dark energy reminds us that the universe is a dynamic and ever-changing place. Its influence on the distribution of matter, the stability of planetary systems, and the potential for interstellar communication adds layers of complexity to the quest for extraterrestrial life. Yet, it also underscores the resilience and adaptability of life itself, which might find ways to thrive even in the face of cosmic challenges. With these ideas in mind, let's now delve deeper into the Fermi paradox and how dark energy might help explain the apparent silence of the cosmos. Now, as we turn our attention to the Fermi paradox, let's consider how dark energy might play a role in this enduring cosmic mystery. The Fermi paradox asks a simple yet profound question. If the universe is so vast and filled with countless stars and planets, why haven't we found any evidence of extraterrestrial civilizations? Dark energy, with its influence on the expansion of the universe, might offer some intriguing clues. One possibility is that dark energy's accelerating effect on the universe could make it increasingly difficult for civilizations to communicate or travel across vast distances. As galaxies move farther apart, the time and energy required for interstellar communication or exploration grow exponentially. This could mean that even if advanced civilizations exist, they might be too isolated to reach out or detect one another. Imagine trying to send a message across an ever-widening ocean. Eventually, the effort becomes too great and the connection is lost. Another angle to consider is how dark energy might affect the lifespan of civilizations. If the expansion of the universe leads to the depletion of resources or the destabilization of planetary systems, as we discussed earlier, it could limit the time window in which civilizations can thrive. Advanced societies might rise and fall before they ever have the chance to make contact with others. This idea adds a layer of urgency to the search for extraterrestrial life. What if we're racing against the clock of cosmic expansion? Dark energy could also influence the distribution of life-supporting planets. As galaxies become more isolated, the chances of finding habitable worlds in densely populated regions decrease. This means that civilizations might be spread so thinly across the universe that the likelihood of two of them existing close enough to interact becomes vanishingly small. It's like searching for a needle in a haystack that's growing larger every second. But perhaps the most thought-provoking idea is that dark energy might shape the very nature of intelligent life. If the universe's expansion limits the ability to explore or communicate, civilizations might turn inward, focusing on survival rather than exploration. This could lead to a universe filled with intelligent beings who are aware of their cosmic neighbors but unable to reach them, creating a kind of cosmic loneliness. As we ponder these possibilities, it's clear that dark energy adds a fascinating dimension to the Fermi paradox. It challenges us to think not just about where life might exist, but also about the conditions that allow it to connect and thrive. Could dark energy be the reason we've yet to hear from other civilizations, or is it just one piece of a much larger puzzle? These questions remind us that the search for extraterrestrial life is as much about understanding the universe as it is about finding others within it. With this in mind, let's now revisit the Drake equation and explore how dark energy might influence the factors that determine the likelihood of intelligent life in the cosmos. Now, as we shift our focus to the Drake equation, let's explore how dark energy might reshape our understanding of this iconic formula. The Drake equation, first proposed by astronomer Frank Drake in the 1960s, is a way to estimate the number of active, communicative extraterrestrial civilizations in our galaxy. It considers factors like the rate of star formation, the fraction of stars with planets, and the likelihood of life developing on those planets. But what happens when we introduce dark energy into the mix? One of the key variables in the Drake equation is the average lifespan of a communicative civilization. Dark energy's role in accelerating the expansion of the universe could directly impact this factor. As galaxies drift farther apart, the ability for civilizations to maintain contact over vast distances diminishes. This could mean that even if intelligent life arises frequently, the window for communication might be incredibly narrow. Imagine civilizations blooming like flowers in a field, only to fade before they can ever reach out to one another. Another variable to consider is the number of planets capable of supporting life. Dark energy's influence on the large-scale structure of the universe could affect the distribution of habitable worlds. As cosmic voids grow and galaxies become more isolated, the density of life-supporting planets might decrease. This could mean that even if life is common, it's spread so thinly across the cosmos that the chances of two civilizations coexisting within reach of each other are slim. It's like trying to find a friend in a city that's constantly expanding. The farther apart you are, the harder it becomes to connect. Dark energy might also play a role in the development of intelligent life itself. If the expansion of the universe leads to the depletion of resources or the destabilization of planetary systems, as we've discussed earlier, it could limit the time available for civilizations to evolve and thrive. This adds a layer of complexity to the Drake equation, suggesting that the conditions for intelligent life might be even rarer than we once thought. It's not just about finding life, it's about finding life that has the time and stability to reach a level where it can communicate across the stars. Finally, let's consider the fraction of civilizations that develop technology capable of interstellar communication. Dark energy's effects on the universe's expansion could make this step even more challenging. As distances between stars grow, the energy and resources required for communication or travel increase exponentially. This could mean that even if civilizations develop the technology to reach out, the vastness of space might render their efforts futile. It's like building a bridge that keeps stretching longer and longer. Eventually, the task becomes impossible. By incorporating dark energy into the Drake equation, we're forced to confront the possibility that the universe might be both more expansive and more isolating than we ever imagined. It challenges us to rethink not just where life might exist, but also the conditions that allow it to connect and thrive. Could dark energy be the reason we've yet to hear from other civilizations, or is it simply one of many factors shaping the cosmic landscape of life? These questions remind us that the search for extraterrestrial intelligence is as much about understanding the universe as it is about finding others within it. With these insights in mind, let's now turn our attention to the final thoughts on the mysteries of the cosmic dark energy era and what they mean for our understanding of the universe. As we bring our journey through the mysteries of the cosmic dark energy era to a close, it's clear that this enigmatic force holds the keys to some of the universe's most profound questions. From the accelerating expansion of the cosmos to the fate of galaxies, black holes, and even the potential for extraterrestrial life, dark energy weaves itself into every corner of our understanding. Each mystery we've explored, whether it's the Hubble tension, the vacuum energy paradox, or the role of dark energy in shaping the cosmic web, reminds us just how much we still have to learn. These aren't just scientific puzzles, they're windows into the very fabric of reality, challenging us to rethink what we know about space, time, and existence itself. The quest to unravel these mysteries is far from over. Scientists around the world are working tirelessly, using cutting-edge technology and innovative theories to peel back the layers of the unknown. Every discovery, every observation brings us one step closer to understanding the true nature of dark energy and its role in the universe. But as we've seen, each answer often leads to even more questions, keeping the flame of curiosity alive. So, what does all of this mean for us? It's a reminder that the universe is vast, complex, and full of wonders waiting to be uncovered. The mysteries of dark energy aren't just for scientists, they're for anyone who's ever looked up at the night sky and wondered what lies beyond. They invite us to dream, to question, and to explore, and who knows, maybe one day you'll be the one to help solve one of these cosmic puzzles. Before we go, let's leave you with this thought. If dark energy is shaping the fate of the universe, what role do we play in this grand cosmic story? Are we merely observers, or do we have a part to play in unraveling these mysteries? Share your thoughts in the comments below. We'd love to hear your ideas and theories. And if you're as fascinated by the universe as we are, don't forget to like, subscribe, and hit the notification bell so you never miss a journey into the cosmos. Together, let's keep exploring the greatest mysteries of all.